All right, I think we're live. So hi, everybody. It's Dr. Zhu and Dr. Mertz again, here to talk to you a little bit about what's been going on in the class. We had a few questions posted to our discussion board, but if you have more questions as we're going, Chris over here, our TA, he's off the camera, but he's going to be checking the discussion boards, and if there's any questions that come up, feel free to type those in, and we'll try and answer those as we go. First of all, it's hard to believe that we are already basically 5 weeks into this, but you're just finishing up your Devils project. The Devils project was meant to be something where you get to explore kind of your own interests, identify a problem starting from the very beginning, and then apply the engineering design process and in a smaller project to come up with a theoretical design for a solution. And you learned a lot of skills along the way. We want to reinforce those skills as we start going into the next project, which is the disaster relief project. And interestingly enough, the two questions that we had in our discussion board forum were related to kind of disaster relief in those settings. We as engineers deal with a lot of very big problems. So when we're looking at problems on the scale of disasters, natural disasters, there's a lot of possible things that we could do to help that situation. Not every design that we're going to come up with solves every single problem, but if we can just solve part of it, we can be part of a larger solution. So for our disaster project, we are going to be designing an aircraft that may benefit people who are in those kinds of situations. And again, there's a lot of different ways that we could apply an aircraft to help out in these kinds of situations. And don't worry if you've never designed an aircraft before. Most of you probably haven't. That's perfectly fine. We're going to teach you everything you need to know along the way. You just have to be curious enough to kind of learn as we're going. And we're happy to help you as we go through this. Can you remind me, what were the questions from the discussion board? Do you have those pulled up?
Yeah, so the first question is related to kind of stuff in Peru. This person says, in my country, Peru, at different times of the year, there's different types of disasters due to overflow, rains, earthquakes, and there's continuous prevention campaigns. And their government created an agency that would be responsible for providing official information on the disaster issues. So how can you kind of rope these insights into what we're doing in the project?
Yeah, the fact is that there are regions of the world that experience a lot of different problems, and it's not just one kind of disaster that we're solving for. So what I want you to think about is we want to come up with a solution, but we want to come up with something that is helpful for as wide of a range of problems as might be experienced in that specific location. So in our project, we actually do model that. We talk about, what are the frequencies of hurricanes or tornadoes or wildfires or whatever might occur, and maybe you could come up with a solution that solves more than just one particular disaster. And Peru is a great example. The example that you gave is a great example of that, where there's multiple things going on, and we want to come up with something that just helps. Again, we don't have to solve every problem, but we have to identify a specific problem within that we're looking to solve. So yeah, it's part of it's going back to the customer or the problem definition, and just realizing that we can specify on a specific problem to solve, and we don't have to do everything. As far as how the class is related, the skills that we use as engineers can be used on any problem. So whether that's the modeling skills that you've learned, whether that's problem definition skills, whether that's technical communication skills, all these can be applied to any problem that we might want to address. The key is to try and follow along with that engineering design process. And as you get more tools, like as you get more modeling tools or you learn something new, it's just about creatively applying that to your particular problem. So we try as engineers to break down these more complicated problems into smaller things that we can actually actually work with. So for me, for example, as an aerospace engineer, I wouldn't be designing an entire aircraft by myself. I might be just designing the wing shape, or I might just be designing the landing gear, or even a component of the landing gear. That's the kind of fine details that we get to as engineers. And so, you have to kind of break the problem down into smaller systems, smaller things that you can solve, and then come up with solutions to those smaller things. And when you add them all together, then you have a big impact.
I think that response kind of relates well to the other question, which with more hurricane damage, some of the damage occurs due to poor building codes and bad event handling strategies. So, what kind of things can be done to ensure the damages aren't as wide scale, and like there can be a faster recovery process in some of these areas?
Yeah, and I think there's two aspects to that we have to think about. One is, what do we do after something has happened? And there are problems that are associated with how to clean up after a big hurricane, or like Irma, or some of these other ones that we've experienced around the world, or some of the other natural disasters that we've experienced around the world. So there's the cleanup issue, but sometimes we can actually forecast what problems might come up. And in that case, how do we design to withstand those situations? Maybe we can design earthquake-proof buildings. There's examples of that in China, where buildings have been standing in earthquake regions for centuries. And what technologies were they using to help make these buildings earthquake resistant? And in which case we don't have to repair afterwards. Same thing is true with hurricanes and tornadoes. There's building codes that are set to a certain level. How can we inform those building codes to improve their ability to resist some of these natural disasters? So there's two aspects. We can help solve the problem once it's already happened, or we could also look at how we could prevent further damage from happening by creating appropriate designs. And I know I'm talking a lot. I don't know if you have anything to add.
Definitely. So as a mechanical engineer, and I know a lot of civil engineers have been working to design buildings and other structures to prevent failures from happening in the first place. So we look at, possible failure modes, how could failure happen, what would cause those failures to happen, and what type of material can we use, what type of analysis is needed to make sure that our design is strong enough, it would be resistant to, vibrations from the earthquake or other types of things that could happen during a disaster. So yeah, that's definitely a very important aspect of engineering, especially in the area of mechanical engineering and civil engineering. And another thing that I wanted to mention, because it seems both of these questions are from students who live in an area that may be more prone to natural disasters. So you might be more familiar with, what could happen during or after a natural disaster. But we might also have students who may not have experienced this, and that's a good thing. But for right, but for this project, don't worry if you don't have much knowledge about that, because we have provided a few different scenarios with some details that you could look into. And the scenarios we have provided include like an earthquake scenario, a tornado, a wildfire, etc. So there's information on that, and we have a few videos and interviews that you could take a look at. And all of these can be located under the disaster relief mem page, I believe. Yeah.
Yeah, there's a whole unit that has all the information, and in week 6 we direct you to that unit. So there's links provided. Just keep going through week 6, and you can click on the links, and it'll take you right there.
Right. And this does sound like a large project, because you're going to be designing an aircraft, and that's a very complicated system, as Dr. Merz has just mentioned. And but don't worry, during the next few weeks, we will take one step at a time and walk you through all the processes. And you will focus on one subsystem at a time, and eventually put everything together and have a final design. For example, during week 6, we will give you an overview of this project, and you will do problem definition. So you will dig deeper into the problem and learn about, what could happen, what are some of the specific needs, what are some of the opportunities, how can an airplane help in a natural disaster. So you will really come up with a good problem definition and requirements and criteria. And then I believe during week 7, we will talk about modeling. And modeling, being able to create models and use the insights gained from those models in the design process is a very important thing for engineers, because we don't just go do trial and error. We apply the principles of math and sciences and use that knowledge to help us, make design decisions and come up with, and test our design ideas as well, because in the real world, we can't just create a building and test it and find out maybe it doesn't work and then create another one and test it. That's very unrealistic and expensive. So we can use models and the results we get from the models to help us, do those testing. So more specifically, we'll be talking about 2 different types of models. Descriptive models, which can be used to help us describe something or some aspect of your problem or your design. We will also talk about predictive models. That is what we can use to predict the performance of a system or part of the system under certain conditions. So during week 7, we will give you an overview of modeling. And then during the next few weeks, we will apply different types of models to come up with designs of each of those different subsystems. For example, I think Dr. Merz can maybe talk about the next week.
Yeah, so you've already learned some of these skills. So when we're talking about, descriptive models, one of those is like a CAD model. So you will have the opportunity to look at a CAD model of your airplane and develop a CAD model of your airplane if you so desire. You don't necessarily have to. Some of you really liked Fusion 360. You want to continue to use that. Great. Some of you already knew AutoCAD and some other software and you wanted to use that. That's perfectly fine. Or if you just want to draw it out by hand, that's also perfectly fine. Remember that we did provide some other software that's available to you for free that you can use online that we didn't necessarily teach, but the topics are very similar. You can kind of tweak your knowledge and apply it to some of these other types of programs. But as Dr. Zhu said, once we start descriptive modeling, we also have to talk about predictive modeling, right? And so I've already helped generate, along with our design team, some mathematical models for you to apply. So you don't have to understand the math, you just have to be able to play with our simulators. And so we've developed a number of different simulators to help you model different parts of the aircraft. So one subsystem that you're going to be working on is the wing design. And for this, we've developed a wing simulator that will allow you to try out different parameters, see how that affects the shape of the wing, and how that affects things like lift and drag that you'll be able to then use for your overall aircraft simulator, which we've also developed for you. So you're going to be able to put values from these tests that you're going to be running into some of these other simulators and simulate your airplane performance. So wing is one aspect of that. So my background is in aerodynamics, love it. And so I've created some aerodynamics simulators. Dr. Zhu, she's a mechanical engineer. She's developed some structural simulators for the wing.
Yes, so inside of the wing ship, you have what is called a spar, or it's actually called a beam in structural analysis to support the load that could be applied onto the wings. So during, I believe that's week 9, we will discuss some basics of structural analysis and what are beams, and how can we design a beam that is strong enough, meaning when you apply some load to it, it could withstand the load without failure, and stiff enough, meaning it won't have excessive deflection or deformation, meaning it won't change its shape or size like excessively. So how can we do that? How can we come up with a beam design to support the kinds of loads that are applied to our aircraft wing? And again, like Dr. Merz mentioned, you don't need to fully understand the mathematics behind those things, but I have come up with a simulator that you could use to play with the cross-sectional shape and parameters of your beam and material that you could select to use, and see whether what you have selected could make sure that your beam is going to be strong and stiff enough for your aircraft design.
Yeah, remember, modeling is just one portion of the engineering design process. And the engineering design process is iterative. We go through a lot of different loops, right, of this design process. So as you're learning new things from these simulators, your design is going to change. The important thing to remember is that you're always designing for a client. You have a purpose that you've defined. You have requirements that you need to meet. And then you have criteria that will judge whether or not you've come up with a good design or not. So as you're going through these simulators, don't get lost in the details. Be curious, try out different things, even things that are just way out there. It doesn't hurt to try it, right? You never know when you're going to find something awesome. But just remember that you're going to be iterating through this process as we go through. One of the other subsystems that you're going to be developing is an automated system. So much of engineered products in the modern world have some kind of automated component, whether that's a smart home, whether that's your car and you have your navigation system, or you're linking to your phone. And a lot of you have expressed interest in like Internet of Things kind of opportunities. Well, now it's time to learn a little bit about how we accomplish that. So I want you to think about how we might automate some portion of the function that you want your aircraft to do. We're not going to be able to do it completely, but the purpose of this is to use a computer to kind of be the brains of your automated feature. And so we're going to learn about a microcontroller called Arduino. And we have a simulator online that you'll be able to actually build circuits that are controlled by your Arduino. And it's going to sense certain things, and it's going to do certain things based on what you're reading. And so that's going to be a really fun couple weeks. We'll talk about how to do that. We'll train you how to do that. But once you understand the basics of Arduino programming, it opens up a whole new realm of things that you can do in terms of automation. And maybe you want to apply that to maybe your own home and create your own smart home using some of these automated features. So once we get to week 12, we've gone through every single sub-function. So everything that you kind of need to design, we've introduced you to all of those different things. And so then it's just a matter of trying to put it all together. So once we've broken it up into parts, then we have to realize, okay, these are parts of a larger design, and we have to eventually get them all back together. And so when you do that, again, there's going to be more iteration that occurs. Maybe you have to go back to some of those weeks, some of those simulators, and try out new things as you've been designing different parts. But it's a part of the design process. Don't get frustrated by it. It's an opportunity to continually improve your design. So once we get to that point, then we're going to start testing.
Yes. So testing in any design process is a very important step, and it should occur throughout, and especially in the end, because how can you make sure that your design does satisfy all the requirements and the criteria? Then project testing is what we do before we can confidently deliver our product to our client. So during week 13, we will talk about project testing, and we will discuss how to write a test procedure that we could use then and pass on to a test engineer. I just want to highlight that during that week, we have a day in the life video where we interviewed a test engineer, and he has discussed, what it is like to be a test engineer. It's actually something that maybe a lot of you are not familiar with, but it's actually a pretty cool career path. So for those of you who are curious, definitely make sure that you check out the day in the life video in week 13.
Yeah, and then we're going to wrap up the project by looking at the financial feasibility of it. So we're actually going to look at could your design make a profit, or could you actually build your design with a reasonable amount of money? And so we'll talk about basic finances within engineering projects, and you'll be able to evaluate your solution on that criteria as well. Now, I know this sounds like a lot, and it is. It's a 10-week project, so it's all this information is going to be spread out over a good 10 weeks. But it's important for you as you're going through this to stay on top of everything. So don't put off those memos that you're going to be writing for each of these subsystems. Don't be putting off the design work of each subsystem. Design as you go. If you put off things, if you try and design the entire thing in the last week, you're going to be stressed out. You're not going to be able to get a good design. Things just aren't going to work. So do pace yourself as you're going through this. Again, we've broken up this complicated problem into smaller bits that you can solve one step at a time. So hopefully you're seeing that we're going to walk you through this process. We're here with you the entire time. Be posting questions as you have that. There's going to be opportunities to show off what you've been able to come up with, discuss with your fellow course mates what's worked, what hasn't, so that they can learn from you and you can learn from them. So pay attention to those. And again, hopefully this is a fun experience. The other thing we want to point out is that while this is one kind of project, disaster relief project of an airplane, it involves multiple engineering disciplines. So whatever discipline you might want to be involved in, these skills that we're gaining by doing this project are applicable for a lot of these different professions. So don't think, oh, this is just an aerospace engineer's problem. This is a lot of different engineering that's going on into this. And so hopefully you can see that we work in multidisciplinary teams as engineers. We do a lot of different things. We learn a lot of different things. We have to be able to apply knowledge from different disciplines to a larger project.
I guess I wanted to add that throughout the project, we have a few project memos that are designed to help you document and walk through, the entire design process. And Dr. Merz has already mentioned that, make sure you stay on task. I also want to mention that for each project memo, you will have an opportunity to evaluate your classmates' work, and your work will also be evaluated by some of your classmates. So I just wanted to encourage you to definitely participate in that and make sure you do give each other some feedback.
Yeah, it's a professional skill to give good feedback to your peers. And so this is done in industry, and we want to model that here in this course as well. So if you want good feedback to help you improve your design, make sure that you're giving good feedback to help others improve their design as well. Chris, do we have any questions that have come up?
Fortunately not.
No? Okay. So this is a class that is really one of those things that if you put a lot of effort into it, you're going to get a lot out of it. You're going to be learning a lot of new skills throughout the next 10 weeks. And so be paying attention also to those ePortfolio, documenting those skills so that in the future, if you want to show off what you've done in this FSE 100 class in GFA, hopefully this is something that you'll be proud of at the end. So make sure that you're documenting all those skills, because these are valuable skills to have. So I think at this point, if we have no other questions, we'll just say we're glad to have you in the class. We've been happy to see a lot of participation. So hopefully you continue to do that. For those of you, if there's anybody who hasn't really been participating recently, now's a good time to jump right back in as we start this next project. So be paying attention to those discussion boards. We'd love to see more of those posts going out. And again, we want you to feel supported. We want you to know that there are people around the world that are going through this course with you, and we want to help you work through this process. It takes practice. Designing something from scratch can be very overwhelming and daunting. And especially at the beginning of a project when we're going to be presenting you with a lot of material all at once in week 6, try not to get overwhelmed. Just remember that we're going to help you through this process. We're going to kind of walk you through step by step, and you can do it. We want you to know that as engineers, we can tackle big problems, and this is a big problem. We're going to walk through the engineering design process together, and ultimately you're going to be able to imagine, design, and engineer a solution that hopefully will solve a problem that may exist in the real world. So this is a real world problem. We're just simplifying it down into this context.
Well, I guess as we wrap this session up, I just wanted to say that I have seen some of your CAD models from your Devils project, and I am really impressed with those. So you've come up with some really interesting, or you've identified some really interesting problems and important problems to solve, and your designs are just great. And I'm really looking forward to seeing your designs for the next project. Yeah.
All right. So thank you for joining in. If you're not joining in live, thank you for watching this video, and we will see you at the next live session. Bye.
Thank you. See you then.